When we have two different metals and we are linking them together so that we can take advantage of their um, cell potentials, right? Their different tendencies to gain or lose electrons. This potential difference can lead to something known as the electromotive force, and common name for that would be the voltage. It can generate a voltage. And so this cell potential is referred to as E sub cell, and it's measured in volts. And a volt is equivalent to 1 joule of energy per coulomb of charge. So think of it as like the push that's behind the electrons. So to measure these potentials, we use a reference known as the standard reduction potentials for elements. And there's lots of different variations of this. This one is from your textbook. We'll look at another one that's similar to the one that's hanging on the wall in our classroom. But what the standard reduction potentials do is it compares against a reference value. And the reference value that's typically always used is hydrogen. And if you look here, you can see about 2/3 of the way down it says 0 defined, and it's for the reduction of hydrogen ion from hydrogen plus 1 to hydrogen in its elemental state. And so taking that reference as our 0 point, all these other reduction reactions are measured compared to that under standard conditions. So solutions are 1 molar concentration, gases are measured at 1 atmosphere pressure, and it's at 25 degrees Celsius, which is not standard temperature and pressure. Standard pressure 1 atmosphere, but it's a different standard temperature than gaseous standard temperature. And so how do we read this? How can we use this? Well, because it's a standard reduction potential table, the more positive the value is, it means it's more favorable to be reduced. And the more negative the value is, that means it's less favored to be reduced. Therefore, it's more favored to be oxidized. And that's really kind of the important piece for us, since the reduction potentials are typically presented in this form as reduction potentials. And so whatever the more standard negative reduction potential is for that substance is what will be oxidized, and therefore that's what's going to be serving as your anode. Now, it's typically shown as a standard reduction potential table, but it doesn't always have to be. It could be standard oxidation potentials. But to get that, it's as simple as negating what you get for the standard reduction potential. So you want to watch your wording. They may switch things up and say the oxidation potential just to see if you're paying attention. So if we take a look here for the voltaic setup using the following half reactions, identify which electrode is going to serve as the anode half cell. So we want to look for zinc and iron, and we find them both here on the lower part. And so we see that zinc actually has a more negative standard reduction potential, so that means it's going to be the one that's oxidized, and therefore the zinc will be at the anode. Now it's asking for the oxidation cell potential. So the reduction cell potential for zinc is negative 0.76 volts. So the oxidation cell potential will be the opposite of that. That'll be negated, so it'll be positive 0.76 volts. For the remainder of these, some of these species are not on this chart in particular, but they are on the wall chart that we have in the classroom. So I'm going to put that up here. I'm going to give you a moment to find the standard reduction potentials for these two and see if you can determine what's going to serve as the anode, and then what would the oxidation cell potential be for those. So hopefully you found these for the anodes and their corresponding oxidation cell potential values. All right, so once we identify what is going to be serving as the anode, the other material will then be serving as the cathode, and we can calculate just how much voltage will this particular combination be able to generate. And so in order to find the cell potential for any pair of half reactions, you have to subtract their individual reduction potential values. And the equation you want to remember is that E cell is going to equal the cell potential of the standard reduction potential of the cathode minus the standard reduction potential of the anode. And so keeping that in mind, okay, we're looking at the same pairs of half reactions. We indicated that zinc, okay, had a standard reduction potential of negative 0.76 volts. Iron was negative 0.44 volts. So the more negative is going to be the one that's serving as the anode, so that's the zinc. So therefore, we're going to find the cell potential for this pair of half reactions by taking the reduction potential of the cathode, which is the iron in this case, so negative 0.44 volts, minus the standard reduction potential of the anode, which is the zinc. So that's the negative 0.76 volts. Watch your signs. Signs get you in all kinds of trouble if you're not careful with these calculations. So you're subtracting a negative, so that makes it a positive, and that will give you a positive 0.32 volts. All right, if we look at the next one, aluminum and magnesium. Aluminum has a standard reduction potential of negative 1.66 volts. Again, magnesium's not on this chart, so we'll go to the wall chart that we have, and magnesium has a standard reduction potential of negative 2.37 volts, so that is going to be oxidized and therefore serve as our anode. To find E cell, E cathode minus E anode, so we're going to take negative 1.66 volts, that's from the aluminum cathode, minus the negative 2.37 volts from the magnesium anode, and that's going to give us a positive 0.71 volts. Go ahead and pause the video, try these next two on your own, and then restart to check your answers. Taking a look at these, all right. Looking at our standard reduction potentials, we see that lead is going to act as the anode. So when we calculate the standard cell potential here, you should get 0.65 volts. And for the final example, we see that both of them are positive values, but that means that silver is the one that's more negative, so therefore silver is going to serve as the anode. And so when we plug those values in, we should get a standard cell potential of 0.70 volts.